Hi everybody, another geology video from the campus of Central Washington University. This is Discovery Hall. You know that by now, I think, don't you? And today we visit with Walter Szeliga, longtime student, now professor here in the geology building. Walter, take it away. Okay, young man, we're rolling.
All right.
Let's take a walk up this way. My God, you're an institution now. You've been here for so long, it feels like. Like, when did you show up here as a grad student long ago?
I got here as a grad student in 2003.
2000,
Seriously,
almost
yeah.
20 years ago.
20
man.
years ago.
And you were coming from where?
University of Massachusetts, Amherst.
So, big journey out here to Ellensburg. Now, how did we get on your radar screen? What attracted you to come here to do the grad program?
I was actually just on a lark, I managed to do you could do a semester abroad at home.
Yeah.
And so I did a semester abroad from University of Massachusetts to Oregon State University, go Beavers. And while I was at Oregon State University, I experienced the 2001 Nisqually earthquake.
Okay.
And I was hooked. I said, I'm going to go back out there where I can feel some more earthquakes. That'll be fun. So I searched around and I looked for grad programs that were doing interesting work with earthquakes. And so I found Central Washington University at the time was doing interesting work with earthquakes and GPS. So that's what I came over to work for.
Got a master's degree here, continued on, got a PhD, University of Colorado, I do believe.
Yep.
And then you found yourself back here, so that's a first. What drew you to come back? What was the draw to get you back here as a professor?
It's a nice, quiet town to raise kids in.
That's a good answer. I agree with you.
It is. It's a nice trade-off between. I have been to small universities. I've been to really large universities. They both have their pluses, but you know, in terms of raising a family, this is a nice town, nice, quiet place.
Well, you are a high-powered guy, and you do amazing research, but you're also in with our students on a regular basis. So, obviously, we're doing these videos to try to communicate who we are and try to get more folks to come and major in geology, so they would see you in the classroom. Like next year even. What are you planning on teaching? What level? It's a sophomore class, so it's a 200 level class, but you can still take it in your freshman year, I believe. I don't think there's any restrictions on earthquakes, tsunamis, and landslides. Yep. That's, I think it's called 203, Geology 203. Got it, yeah, required for the major, good.
And then I have some upper level courses that I'm teaching. I have a 400 level course in seismology that I'm teaching as well.
Well, I mean, you do have a wide variety of interests, geology and otherwise, and you know, in addition to all your talent and your hard work, you were instrumental when we. Oh, that's a pun, actually. You were instrumental.
I like what you did there.
Wow. When we kind of tried to get moving with this building, and you know, we talked to Rex about the rock garden a couple weeks ago. And
that was a fun project too.
Well, you were involved in that a little bit?
That was a fun project. Driving around the state trying to get rocks from the side of the road that the DOT said we could move. That's good. Okay.
But we're going to show off a couple things inside of the building, and so we're going to encourage people to come. Continue to encourage people to come. So yeah, it's a beautiful day, but we're going to go in the east entrance here, and one of my favorite things in the building, maybe my favorite thing in the building, is a direct result of your efforts to get that going. Can you give us a teaser before we actually see the thing? What are we going to see when we first go in on the left?
So in one of our old home buildings, beautiful Lind Hall, yep. We had a three-dimensional contour relief map of the state of Washington. And it was very nice, but it was made out of sections it was plastic, and it was made out of sections that were all thumbtacked together into the state. It's amazing that somebody had the patience to cut them all out so precisely and thumbtack them together.
That was me!
Because they didn't come that way originally, right. And it looked great. And so when we moved over here, we wanted to have a map that was similar, but we didn't want to just pull the thumbtacks off on the old map and then right. put them on the new wall in such a nice new building. And so I tracked down a company that makes three-dimensional maps, and I helped design the layout of the map, the projection of the map, how tall it was, and then we commissioned a company to actually produce it.
Well, I'll put the link to the company in the description below, and the work is just amazing. And I I don't know if you know this, Walter, but I use that map almost like a indicator of who I want to kind of hit up when I'm walking down the hall. Because if there's a 19-year-old student who's like on their own volition stopping at this map and checking it out, I go, oh, this guy, I like this person. I like this young lady. I want to go talk to them, see what they've got to say. Well, here it is, right here on the left. Oh, my Lord. Just seeing it through the camera lens here makes me more excited than ever. So how would you describe, or what's the techniques, first of all? What do you, how did they create this for us?
So it's a pretty thick map. It's actually mounted on wood, but beneath the wood there's sort of a block of a dense foam.
Okay.
And they make these smaller panels, and for each of the smaller panels they actually use a laser to carve the topography into the foam, and then they coat the entire map, and then they, I think, sonically weld all the pieces together and then ship it up here.
And so you say you did some measurements or some calculations, like what were you trying to figure out? Like how bumpy it should be?
Yeah, basically how bumpy it should be. So our old map had Rainier was a certain height. Rainier is the one that pokes out the most.
Right.
And so we wanted to make sure that Rainier would stick out, but not so much that people would walk by and knock it off, and not too little that you would miss all the other cool things that are in the state.
Right.
So we measured how tall Rainier was, then we figured out how big that would force the rest of the map to be. And we also wanted to cover a little bit more than just Washington, because we don't just study the geology and stop at the Columbia River or stop at the Canadian border. So we wanted to include a little bit more and make the map as big and have as much pop as possible. And so the map does continue down to at least Mount Hood, almost to Mount Jefferson, doesn't quite include it. And it continues up through Vancouver, British Columbia. It includes a little bit of the Fraser River. It also goes all the way out and includes the northern part of Idaho and a little tiny corner of Montana, and then out into the ocean here. Couldn't quite include the trench. That would have been nice, but we wanted to include as much as possible.
Well, sure. So the times that I've sat here and stood with people, they're asking about like pretty basic questions, like, is this hand painted or is this some sort of digital overlay? You're saying it's some sort of imagery from...
Yeah, so I believe this was all, so it's all actual cloud-free imagery from NASA. I think it's the NASA Whirlwind data set.
Oh, wow.
They go through and they piece together all these photographs of the whole planet at around the same season for the whole planet in times when there are no clouds. And so this is a rare cloud-free day in Washington for the whole entire state of Washington. And so this is an actual spring or summertime image from the state, but it's all stitched together.
Wow. Well, it has survived the 5 years we've been in here.
It has.
I mean, I hope it has lasting power. I don't know. It's more durable than the plastic thing you were talking about before.
That's for sure.
We would literally have people up here fondling Mount Rainier until like there'd be a big hole.
And I think, if I remember correctly, the old map actually still had the complete Mount St. Helens, and at
It
some
did.
point, yeah. And so this one does not have a complete Mount St. Helens. It does. It is a post 1980 Mount St. Helens. But I guess we could have done a pre-1981 if we wanted
Sure.
to.
Well, actually, improv time. So since we're looking at this map, you've had a large role with the Panga network.
Yeah.
And can you give us a sense of the density of the geodetic array on this map? Like, how can you use this map to give us a sense of how many stations exist and how often they're pumping data into this building?
Well, one of the goals with the Panga network is to position ourselves so that we can watch the actual plate deform, the North American plate deform, and we can use it to catch any large earthquakes that happen along the West Coast. And so to serve those goals, we have far more stations on the west side of the state than we do on the east side of the state. And you can even see this here. I mean, the entire western part of the state has all these really neat geologic features, from the Olympic Mountains all the way through the Cascades, all the way out here to the Trench. Things get more interesting as you get out here because you lose the tree cover as you get out to the desert. And so we do have a little bit of a density of the network here in the Ellensburg area, mostly because it's close to us and we can go out and service instruments. But the further you go to the east, although we have the fantastic Rocky Mountains here, the amount of signal you see from the GPS goes way down by the time you get to Montana. That being said, we partner with Idaho Department of Transportation, Washington Department of Transportation, Montana Department of Transportation, and we use their sites. They use them for surveying. We scrape the data off the other end, and we share infrastructure. And so we're able to get instrumentation all the way across the northern tier.
And can you confirm that I have been teaching correctly, that the velocities per year for these stations moving is clockwise, and that clockwise rotation gradually decreases, and by the time we get to the north part of this map, those stations are not rotating clockwise much at all?
That is true. Relative to the stable part of North America out towards Iowa, this entire map is, all the ground here is all sweeping clockwise. And by the time you get out to northern Idaho, it's still going, but it's tiny.
I mean, I just can't thank you enough for making this happen. Without you, I don't think this map would exist here. And it's just been such a great part of this building.
No, but every time you take a look at it, there's always a new signal to find, right? Like you can look at this and you can look at the glacial flood topography. You can look at this and you can see the actual glacial scour topography that you have from Lake Chelan. You can see the Cascade volcanoes and how they all lie across the entire Cascades. There's all sorts of neat things to see here each time.
I'm not kidding. If I go to a new area for me and I'm out just wandering around, the first place I come is here.
That's what I did too.
Yeah, I say, oh, God, yeah, I was right here. And there's a drainage to the north. And I know you can do it with other imagery on your laptop or whatever. But
it doesn't have the same. It doesn't have the same feel. This doesn't have any load time, and you can go and zoom in like this, and you can back.
No load time map. Yes.
That's right.
Okay. Well, thank you for that. There's one more thing we definitely want to add with this, and that is heading upstairs. We'll take the scenic route, go up the stairs, a little huffing and puffing. You've had some grad students over the last decade plus. Can you give us a sense of the variety of projects that you've supervised, whether it's grad students or undergrads, actually?
I've had students work on a variety of projects. Oftentimes it's either earthquake or tsunami related.
Okay.
I've had a couple of grad students work on projects looking at GPS and plate motions in Pakistan and India. I've had students working on tsunami modeling for the middle of the Pacific Ocean, the Marianas Trench area. I have a student right now who's working on earthquake swarms in Idaho and in Nevada. So sort of all over the place. And I have a grad student right now who's working on paleoseismic trenching in the Kittitas Valley.
So. On which fault?
It's called the Dead Coyote Fault.
Dead Coyote, that's Andrew.
That's Andrew Sadowski. You can thank him for that.
All right. So you will be trenching, like with a backhoe and the whole thing?
We hope so, yeah.
Well, that's cool.
Yeah.
What's known about the prehistory on that fault? Anything?
Absolutely nothing. That's the whole point of it.
Okay.
We found it Andrew found it with LiDAR in mapping the entire valley, and we found a landowner who was willing to let us dig a trench across their land, and hopefully we'll be able to find something really neat there.
Sweet.
Yeah.
Okay, quick orientation. So you're turning east, looking out the window, and Student Union Building, and so up on the third floor we are, and I asked if Walter could take the sliding glass doors off of this. So this is normally a locked case, but I wanted to really give you the full effect. So this is you designing this, or how would you like to describe what you have here?
Oh no, we had a couple of years ago. We had a seismology class, and we got a little kit together, and we built a seismometer just to show that the inside parts of a seismometer are not particularly complicated.
Okay.
This little red thing at the end here is a children's magnet. It's actually one of the larger magnets. And underneath it, there is a little plastic spool with some yellow tape on it. Underneath that is just speaker wire.
Okay.
And you just spool the speaker wire up, and you suspend the magnet with a spring.
Okay.
And so when the ground moves, the magnet's heavy and it stays still relatively, and the ground moves underneath it. And as the ground moves underneath it, it generates a voltage in the speaker wire, the magnet does, and that voltage travels through the cable all the way up to the screen, and then we plot the voltage on the screen, and that's all there is to a seismometer.
Well, I'm really amazed at the simplicity of this. You must have seen this, somebody else do this? Or,
Yeah.
Yeah.
I've retrofitted it with a couple of other options. It used to have a little damper so that it didn't keep bouncing forever because it has a spring. It was a damper made out of a little washer and some olive oil. But when you leave olive oil in a case that's heated up by lights for months, it doesn't smell so great. So
you heard it here first, folks.
That's right. So we have a little magnetic damper, actually. So these are the really powerful neodymium magnets, and then there's a copper blade. And so that actually magnetically damps the entire system.
Okay.
It doesn't go bad.
So this is not just a little model. This is real.
This is real, and it collects data, and it posts it out to the web. I pulled the glass off, but the glass does have a QR code that we'll show you later.
Okay.
Because we're in the third floor of a building, and it's not the best place to record seismic signals,
right.
And because people walk by this room every day,
yeah.
all sorts of other things get recorded on here, mostly people's footsteps. And so this top part here is the seismometer that we just showed you that was green, and all these little blips are just people walking around the building. Until you get to this blip right here, which is actually an earthquake in Argentina. And that trace continues on for a while. And the reason we know it's an earthquake from Argentina is on the bottom half of the screen, we have a very nice, quiet professional seismic station, one of the real nice expensive ones in Liberty. And so that is actually located in a vault in Liberty in somebody's basement, and there's very little signals from people walking around in the building. If you see a signal on our seismometer and on the remote seismometer, the seismometer in Liberty, you can be sure that it is not just a signal from in the building, somebody walking around shaking the case. And so here you can actually see this is from Argentina.
Well, how did you know Argentina? Did you look at it? Did you notice it this morning and then like ran to your office or something?
No, this was yesterday. Somebody actually told me it was yesterday, and I hadn't even seen it. Okay. Typically, what happens is if you know that an earthquake has happened because it gets posted on the internet by the Global Seismic Network folks. This is the U.S. Geological Survey website. You can usually look at it and then come over here and say, oh, that's probably that earthquake, and you can see what time it happened here. The waves arrive at 23:18 Universal Time, and then you can go to the website and see what earthquake big enough could have been at 23:18 Universal Time. What's more exciting, however, is if you happen to walk by here during the course of the day and you see the trace starting to wiggle, you can look over at this computer and see, are there any earthquakes? And oftentimes there aren't. You're seeing the earthquake, you're seeing the ground beneath your feet move before the Global Seismic Network has had a chance to locate where the earthquake was. And so people will sit here and they'll try to guess, where do you think that earthquake is?
Well, let's get one right now. Come on.
Yeah.
Or did you say there was something from Yellowstone?
There was something from Yellowstone. That was from yesterday.
Okay.
So there was something from Yellowstone this morning. So you can see this is a deep earthquake. There's no surface waves on it, just a P wave, and that's probably an S wave packet. So it's deep, doesn't have any surface waves, and it's far away because these things are spread apart in time. But if we look at a local earthquake or a more regional earthquake, this is not local. Local would look even different than that. So this here's our seismometer that you saw at the beginning of the video, and this is the seismometer in Liberty. This is a magnitude 4 in Yellowstone this morning.
This morning.
Yeah, so it looks quite a bit different. And if you just had our seismometer in isolation, you wouldn't be able to tell the difference between that and the time when everyone's class gets out and the students walk through the hallway. So it's really important to have, if you have a slightly noisier environment, to have a quiet instrument to compare with.
So you did that on purpose?
I did that on purpose, yeah.
So all this noise here is the building generally?
Yeah, and if it gets, there's all sorts of other signals. When it's wintertime and it's windy and stormy on the ocean, this building shakes. The ocean shakes Washington State enough that both of these will actually start picking up the ocean waves hitting the coast. If it's windy and this building is shaking, you'll see this. And this building isn't tall and skinny. It's a big, long, weird shape, but the wind still shakes the building.
And this is?
That is a map that shows how far it is to every other place on the world from a seismic standpoint, and it has a shaded area to show the area that we can't pick up earthquakes from because they are blocked by the core of the Earth. And we do pick up earthquakes all the way up to the edge of that and then on the other side.
That's amazing.
Yeah.
And here's the QR code, which I think is usable, like even in this video. I've heard from people that you can do a QR code through the video. So regardless, I'll put this link down below as well. Can you get up on the roof?
Yeah.
You got another minute?
Yeah, let's go up on the roof.
You are a VIP. I'm just going to keep rolling here. You okay if we keep that case open for a few minutes?
Yeah, I think it'll
Yeah, so this is a live building in the sense that there's this geodetic network. There's processing of the GPS data, and the data's got to get into this building somehow.
Yeah, you're not going to climb that ladder with me, are you?
I don't know.
It's going to be really bright. I should have brought my sunglasses. It's usually unbearable to see up there when we get up there, but we can give it a try.
We'll just at least enjoy the view. Nothing like spontaneity here. If nothing else, I'm showing that we have a ton of good sports in this department. Like, nobody's prepared for anything. I just knock on somebody's door and say, hey.
And we're going to get it on this side.
Oh, okay.
This is like a James Bond elevator.
Well, what do you miss about the old building? Anything?
Yeah, it just had character. I mean, new buildings are super nice, but the old building was an old kindergarten, and my office had this weird stained glass windows in it that had pictures of kids with, rabbits or whatever. I don't even know.
Yeah.
It was crazy, but I like that.
Oh,
Are you ready to be blinded?
Telescopes, I guess, right? Is that what these are?
Yeah,
Physics?
those are telescopes for astronomy class.
All right, we're on the 5th floor, totally restricted access. Oh, damn, son.
Yeah, I told you.
No, I'm loving it. Hang on just a second.
Oh, it's a great view up here.
Oh! The crystalline core of the North Cascades, the Stewart Range. You know what those farmers say? As soon as the snow goes off of Mission Ridge, then you can start planting your whatever. I don't know the last part. But
Oh,
I know
that's never going to happen this year, I feel like.
All right. Well, yeah, I mean, I have no idea what's up here, but oh, I see. All right, so actually looking to the old geology building and the Yakima River Canyon to the south. Sorry, Walter, distracted. Okay.
That's okay. The old geology building actually has a GPS instrument on it. It's too tiny to really see, but it's near the other telescope dome.
Okay.
And that instrument's been operating for 26 years. It's one of the oldest ones in North America. There's been there are a handful that are probably 30 to 35 years old, but that's been continuously operating on that roof and given the position of that roof for 25 years. You think that's not very important, but the whole building has moved. The entire valley has moved, and so having that on there for 25 years, we've been able to actually watch the entire eastern part of Washington move along with it. So.
How much has Ellensburg moved in 25 years?
It's on the order of, I think I did this couple, it's on the order of centimeters. The entire valley itself contracts around 2 millimeters per year. So, not an awful lot, but certainly over 20 years,
come on, that's
it adds
crazy.
up.
It's crazy.
So to get the data in from the coast,
Yes.
I don't know if this is exactly where you were going. Rex and I built the satellite dish. They do not come that way. They come in little pizza wedges, and then we had to bolt it on the roof. On a typical calm Ellensburg day. And in the advent of a really large earthquake, we've learned from other large earthquakes on the planet that most of the data comes in on the cell phone network.
Okay.
But the moment a large earthquake happens, everybody picks up their phone and they call somebody to make sure that they are okay, or to tell somebody that they're okay.
Right.
And it shuts down the cell phone network. And we really want to have that data
I see.
available. And so for our instruments on the coast, the ones that are going to give us the most detailed information of what's happening, if we have a very large earthquake on the coast of Washington, have a redundant backup that goes to a satellite, and then it gets beamed down to the roof here.
God dang.
So we have 2 data streams for all those coastal sites.
Really?
So that we don't lose that data at the very last minute to help figure out how large the earthquake is and where things are needed.
So when we built the building 5 years ago, the role of this network was a big deal, I'm assuming. Like,
yeah.
You had to be on the 3rd floor. You had to have, like, how was this building constructed with the Pango network in mind?
We have a little spot up there to run test antennas, and then we have a pipe that goes down to our office, so we can actually feed antenna cables down and then run instruments to our laboratory, but keep them out on the roof.
And the part where there's data coming in like every half a second or something?
Yeah, we get data every second from the entire west coast of the U.S. through
to
the
this
satellite,
building,
to that satellite dish. Yeah,
to that satellite dish. That's mind blowing. All right. Well, now
you can thank Rex Flake for that. You probably already met him in a different video.
I think they did, yeah.
So not only did Rex and I build that dish, but Rex went out all by himself and built the dishes at each one of those stations and positioned it while I was here in this building, making sure the data was going from the coast to the satellite to our building. But he had to go out in the field and get all those things set up in the weirdest locations.
No kidding.
So.
Oh, you guys make a good team, that's for sure. Well, blue skies and Discovery Hall once again. Thank you, Walter, for your time.
Yeah, no problem.
I don't want to go back inside now, I don't think. It's perfect up here. We should do something up here. We should have a Friday afternoon. We should just all be sitting up here having, maybe this afternoon.